going to perform a first and second derivative study on this function here. Now, with these functions, with these problems, because they're so long, the derivatives are usually not complicated, and functions rather themselves are not complicated. So let's perform a first and second derivative study on this function. So the first thing you want to do is take the derivative, all right? So f prime of x will just be, well, 2 times 3 is just negative 6x squared plus 12x, right? And that will be my first derivative. Now, here's the second point. This is where you start to find your critical points, all right? So you're going to set your derivative equal to 0, and you're going to solve for x. So again, the good thing here is that we could factor. So I could factor out a negative 6x, multiply that by x minus 2, and that will equal to 0. And then obviously you could see where x will be 0 and x will be 2, right? Negative 6x is equal to 0. Divide by negative 6, you get x is equal to 0. And then obviously x minus 2, set that equal to 0, you get x. You get plus 2, right? So these right here will be my critical points. All right. And then what this allows me to do is perform my first derivative study. So I'm going to write f prime of x, and I'm going to draw a line like this. All right. And draw a continuous line like this. All right. Now, this is where I put my critical points on the graph, on the line rather. All right. So I'm going to have a 0 here. I'm going to have a 2. So here's what I do. Now we got to plug in test points to see where the function is increasing or decreasing. And that will give us some idea of, whether we have a local max or local min, right? So over here, my test point would be -1. Test point here, I'm just picking some random numbers between these intervals here. My test point here would be 1. Then my test point here would be 3. So I plug these numbers back into the original derivative. And again, negative 6 times -1 squared plus 12 times -1. Well, this is just equal to -6 minus 12. And that's just going to equal to negative. We don't care about the number. We just want to find a value of the sign. So if this is negative, right, which will give us a -18, well, this tells me that my graph is doing something like this on this interval. It's negative. All right. So let's look at the test point between here. Well, again, -6 times 1 squared plus 12 times 1. Well, this is just equal to -6 plus 12. Well, a bigger positive number, smaller negative number will always equal positive, which means that my graph is increasing on this interval here. How about test point 3? Well, again, -6 times 3 squared plus 12 times 3. Well, that's just -54 plus 36. And that's going to equal a negative number. As you can see, the -54 is way bigger than that positive. So this is negative here, which means that my graph is doing something like this. It's decreasing on this interval. All right. So this is the reason why we draw this line here. All right. So we could say the function, all right, we could say the function is increasing on the interval from 0 to 2. It's decreasing on the interval from -infinity to 0, right? -infinity to 0. And also 2 to positive infinity, right? So this is where my function is increasing and decreasing, right? So this is what my first derivative tells us. So this is what the first derivative study tells us. Now, there's also one more important thing that we haven't mentioned, or local extrema. Anytime you have your functions kind of coming down like this, or making an upward mark like this, this will be a max, this will be a min. So here, here we have a min, and here will be a max. So anytime your function is coming up in the air like this, it will be a max. Anytime they're meeting down, will be a min. Just for argument's sake, if we have something like this, right, then we would have no local extreme at all. But because we have a min or a max here, here's what we write. We have a local min. We have a local min at, well, we have a local min off. I'm sorry about that. Wording is very, very important. So we have a local min off. We don't know what the local min yet is, but we have a local min of some value where x is equal to 0. So we have a minimum of some value where x is equal to 0. We also have a local max of, we don't know that value either, where we don't know that value either. So we also have a local max where x is equal to, 2, as you can see. Now, how do we find those values? We plug in these values into the original function, So in that case, I would have f of 0 and then f of 2 into the original function here. This is where I plug it in, right? And you could just plug this in your calculator or do the work for yourself, either or. But if you plug in 0 into this function here, right? If you plug in 0 into this function here, you're gonna get a local min of -3. As you can see, 0, 0, and this will just be -3. If you plug 2 in, into the same function, you will get 5, right? And so you have a local max of 5 where x is equal to 2, and you have a local min of -3 where x is equal to 0. So remember this step. You plug this into the original function, not your derivative. Now the second derivative, or second derivative study, all you're doing now is just taking the derivative of the first derivative. So we're taking the derivative of this -6x squared plus 12x. And taking the derivative of that, that will just be equal to -12x plus 12. Again, as you can see, 2 comes down, -12x plus 12. So this will be your second derivative. We set this equal to 0, and we solve for what x cannot be equal to. Again, we could move our -12 over here. -12x is equal to -12. Divide by -12, and we get x is equal to 1. All right, so x cannot be 1 in this case. So here's what this x is. This will be your inflection point. So this will be your inflection point. And so we're going to draw a line, f double prime, we're going to draw a line. We're going to have 1 on this. We're going to have our concavity, we're going to have our inflection point here. Now the second derivative tells us where the concavity of the function, whether it's concave up or concave down. So we could just plug in some test point here. So my test point here will be -2, and I'll just plug in some random numbers. And my test point here would be, I don't know, let's choose 3. All right, so I'm going to plug these values into my function. So -12 times -2 plus 12. Well, you could see -12, that's a positive. So this will be a positive number, right? Negative times a negative is a positive, and then you have a positive. So this tells us a concavity. So this is concave up here. It's positive. How about test point 3? Well, -12 times 3 plus 12. Well, -12 times 3 is actually -36, which will be way bigger than -12. And that will just be concave down because that will be a negative number. This will give us a negative number. This will give us a positive number. So the graph is concave up from -infinity to 1, concave down from 1 to infinity. And notice how these match. If you look at how my second derivative on the concavity, you could see that kind of, so you could see the concavity here, and then coming down, you could see the concavity decreasing on this other interval here. So that's another way of checking yourself to know that you're correct. And this would be the first and second derivative study of this function here.